we thought we had 7 hours. Yeah, we thought we had 7 hours difference, but we have 8 hours difference. So it's a bit late here, but it's a pleasure to give the talk. Also, we have a season difference. So this is summer here. You might actually hear the cricket in the background. So I gave different subjects to Jean-Luc, and then we settled for this introduction to large deviation theory. So the goal is to give you, as Jean-Luc was saying, a historical introduction to large deviation theory, and then in the second part show how the theory is applied in statistical physics to study various systems, equilibrium systems, non-equilibrium systems, and then the kind of maths that we borrowed from the theory to study this. So I'm going to have two parts. So I'll start with a bit of history, and then I'll try to explain the basics of large deviations. I'm not going to explain the whole theory, just the main results that we use in physics to study equilibrium and non-equilibrium systems. And I'll use one or two systems just as examples to show you how we use the mathematics to study the properties of these systems. Now, the idea that we have in mind is that we study stochastic systems, so systems that have some kind of randomness, and we want to study typical states or equilibrium states of something that is related to the law of large numbers, something stable. But with the theory, we want also to study fluctuations around these typical states. And this is what the theory is about. So large deviations means large fluctuations. And behind this, we'll see, there's always some kind of scaling limit involved. It could be a thermodynamic limit, it could be an ergodic limit, it could be a low temperature limit. And that limit is important for the theory, and I'll try to explain this. Now, what's also interesting with the theory is that if you look at the history, it's a kind of very convoluted history, entangling physics and mathematics, like many subjects. And if you look at the history, and if you try to trace down really where the theory is coming from in terms of first result, the first result will come from Boltzmann in 1877. And then the theory actually kind of developed, or at least some results that have a large deviation flavor emerge in physics, but it's only with the work of mathematician Cramer in 1938 that the theory really started as a mathematical theory. But then the interesting thing on the mathematical side, which I'm showing here on this slide, on this column, is that the theory evolved completely independently of physics for all that time, from 38 to about the 70s, and then only came back to physics in the 70s and 80s. So you have this movement of the theory and then evolution of the theory, which is really interesting from a historical point of view. And I'll try to give a flavor of this. So I'm going to start actually with the first result that people consider as the first large deviation results. And I think even mathematicians actually agree when you explain to them that this is a large deviation result, and it dates back from 1877. So this is a famous paper by Ludwig Boltzmann, in which he's trying to give an interpretation of entropy, statistical interpretation of the entropy. And this is the first paper where entropy actually appears. And I'm putting here the excerpt from the paper where you have entropy as the letter M, and this is P log P essentially. So the W's are the probabilities and the log is the L. So you have a kind of sum of P log P, which we know is the entropy. So the idea that the problem that Boltzmann considered is that you consider n particles, and so you can label them 1, 2, 3, 4, you have n of them, and then you look at the energy levels of each of the particles. So you can number the energy levels like 1, 2, 3, and then for each particle you say, okay, that particle is in this energy level, that particle is in this energy level. So when you do this, you actually specify the microscopic configuration of the system. You specify what energy level each particle is in. Now, Boltzmann was really interested in the statistics of the system, not in the actual state of each particle, but in the energy distribution. So instead of looking at the configuration, you look at the statistical distribution of the energy levels. So you define this Wj as the number of particles in some energy level J. And the question that Boltzmann addresses is, what is the probability distribution of that energy distribution if we assign some kind of uniform probability distributions on the configuration? And this is the basis of statistical mechanics. This is the first time really that someone was trying to use ideas from probability theory to study a physical system. Now, for this, what he looked at is that this is really, if you assume that there's no interaction between particles, this is just a combinatorial problem. You want to count the number of different ways that you can put n particles in those statistics for the particles, the number of particles that you have in each level. So this is the multinomial factor. We can call this the multinomial distribution. And then what he did was that if you take the log of the multinomial factor, then using Stirling approximation, you can approximate this on the log scale as n, the number of particles, times the sum of W log W. And this is the entropy. This is the entropy of the particle distribution. So what this means is really, when you, with a lot of hindsight, because Boltzmann doesn't use a probability notation, but if you rewrite this in probabilities, it means that the probability of seeing a given energy level distribution, if you draw particles at random, will be exponentially small with the number of particles, and then the exponent is the entropy. So this is the first time that entropy, statistical entropy, appears. And again, here I'm using the modern notations that we have for the entropy, kind of P log P, but what he used there is that WLW, so the log for him is L. Moreover, when he uses the Stirling approximation, he doesn't call it the Stirling approximation. It's got some other name, which I don't remember, but essentially this is something that's there. And it's a calculation we see often now in statistical mechanics. If you open a textbook in statistical mechanics, you have that kind of calculation. And then you also find it in textbooks on information theory. It's very much related also to Shannon's information theory, where of course the entropy appears also for exactly the same reason, in fact, but I'm not going to discuss this. So this is the first large deviation result. And what I mean by large deviation result, and this will be the theme for the next slide, is that we have some probability that scales exponentially with some parameter. Here is the number of particles. And then we have some exponent that we're trying to calculate. So here, by combinatorial means, we're able to calculate the exponent as the entropy. But the important part is that we have a probability that scales exponentially with some parameter. Okay, so this was done by Boltzmann in 1877 for independent particles, what we call in physics the perfect gas. There's just no interactions. And then came Einstein in 1910 asking the following question: how can we generalize now this idea of counting to find probabilities of certain macro states or certain observables of a physical system when we put interactions? In this case, it's very difficult, if not impossible, to actually do combinatorics. So here Einstein wants to generalize the argument of Boltzmann for something more general than the particle distribution. So he wants to consider what we call in physics a macro state, which is just some kind of observable quantities that you want to measure, which is a function of the microscopic configuration of the system. So I'm going to call this M of n. And n, again, is the number of particles. So this is some kind of physical quantity M that depends on the n particles. And what we want to do, as always in statistical mechanics, is to calculate the probability of that macro state, or in other words, also for us, what we do in statistical physics is to count the number of microscopic configurations with a given value of that macro state. And what Einstein did is to say, well, that density of state, what he calls the complexion, actually should behave also exponentially like Boltzmann found before for any kind of system, whether you put interactions or not. And then we're going to assume this as an ansatz that the density of states behaves like this. And then from this, you can basically derive the whole of statistical mechanics and thermodynamics. So this is Einstein postulate. People often see this as a reversal of Boltzmann's calculation in the sense that you're not doing the combinatorics to realize that the probabilities are exponential. You just postulate that every probability that will be related to an n-body system will actually have an exponential form. And out of this, and I'm not going to discuss too much, but this is really a postulate that has far-reaching consequences, because out of this, you can derive the whole of thermodynamics, you can derive the canonical ensemble, microcanonical ensemble. And this is, you realize that this is really the basic postulate of statistical mechanics, for equilibrium statistical mechanics. For instance, if you're looking for the macro state that has the highest probability, in this case, you would maximize the exponent, you would maximize the entropy. And this is something, this was a postulate that was known in statistical mechanics, that equilibrium actually maximizes entropy. But now it's just promoted as something more general beyond the perfect gas, beyond non-interacting system. So here I'm putting the excerpt from Einstein's paper. This is a very famous paper. And this is another result from 1910 now, where we write a probability in some exponential form with some scaling parameter, which happens to be the number of particles here. So these are two results that point to something quite general, that when you're dealing with probabilities of a large system, probabilities behave exponentially. So From these two results, actually, these are very fundamental results in statistical mechanics. And then from that point, statistical mechanics just evolves on its own in physics and become the theory that it is now, which is very useful and taught to all students taking physics. But nobody realized in physics that you can build a theory for these probabilities, that this is actually something general just beyond physics. And the first result that really pointed to something more general mathematically is the result from Cramer. So this is Harald Cramer. Harald Cramer was someone very interested in natural mathematics, in sums of random variables for insurance purposes. So he was, in those days, insurance was very much based on the central limit theorem, where you make Gaussian approximation, but this is not very good for insurance companies because you want to insure yourself from very large events, so very large fluctuations. And assuming that if everything is Gaussian is not a good approximation because you lose a lot of money. In fact, large fluctuations are more likely than Gaussian predictions. And so you want to extend the central limit theorem beyond just Gaussian approximations for the tail of distribution. And this is where the result of Cramer actually came in. So what he does is you consider a sum of random variables where you assume for simplicity that they're independent. So you take independent and identically distributed random variables and you divide by n. So you can see this as a sum of random claims coming with a certain distribution. And what Cramer wants is the distribution of that sample mean. Now to do this, so you have to go through that paper, which is actually written in French. And what he does is that he just introduced the cumulative function and then says, or actually derives, that the probability density of the sample mean will be exponential with the number of random variable, which is small n in this case. And this is the dominant part of the distribution. Then you can derive all sorts of corrections to this. But what's important is that the density has this dominant exponential form, and it's got a certain exponent, which I write here as I of s, and then we call this the rate function. It's also called sometimes the Cramer function. It's this exponent function that tells you how fluctuations actually will be dampened with the values of the fluctuation, but also with the number of random variables. So we see now again this idea that a probability density or probability distribution will have an exponential form approximately. It's not exactly exponential. You have all sorts of non-universal corrections, but what's universal is the exponential form in front. And the rate function is the Legendre transform of the cumulative function. So this is a kind of, call this the Legendre-Frenkel transform, but this is really a Legendre transform connecting the cumulative function to the rate function. So this is the first mathematical result in large deviation theory. If you talk to mathematicians and say, where does it come from? Where does the theory come from? They'll say it's Cramer. But then you can show them Boltzmann, and then they'll just be amazed by the similarity of probabilities. And this is where, again, the interesting history happens. So that was the first mathematical result. Not a lot happened actually on that front. And then somebody else came up in 57 with another large deviation theory, a Russian mathematician by the name of Ivan Sanov, who was also interested in sequence of random variables, but instead of looking at the sample mean, so a sum of random variables, what Sanov looked at is you take a sequence of independent random variables and now you count the number of symbols that you see. So imagine, for instance, that you have a binary sequence. So you have a bunch of zeros and ones that you throw at random with some probabilities, and then you want to count the number of zeros in the sequence you have and the number of ones in the sequence you have. So you can make a vector out of this, the fraction of zeros, the fraction of ones. So this is the empirical distribution. This is the sum of the number of times in the sequence that you see a certain symbol X. This is a random vector. This is a random distribution. If you throw another sequence, chances are you're going to have another empirical distribution. You're going to have different fractions of zeros and ones. So you might be interested in calculating the probability of that vector. And then for IID, it's also a combinatorial problem that you can do. It's the multinomial distribution. And what's interesting is that when you read the paper of Sanov, he just lays out the problem and then follows exactly the steps that Boltzmann followed in 1877. So he says the distribution is a multinomial. I will approximate it on the exponential scale using Stirling approximation. And what he gets is that the probability distribution is approximately exponential with the number of random variable, and the exponent is the relative entropy. If you take P to be uniform, then the relative entropy is minus the entropy. So that recovers Boltzmann result. Now, this is all couched in mathematical notation. So this is this is more rigorous as a result. This is a mathematical result, but the idea is very much the same. And moreover, there's an interesting parallel in that in Boltzmann in his paper will start with discrete systems, and then he would say, okay, how do we treat now continuous states? So instead of looking at discrete energy levels, how can we look at now generalize this to something that is continuous, like the kinetic energy? And he says, well, you just take a discretization of the continuum, and then you take a continuous limit. And in Sanov's paper, you have exactly the same. So there's like an amazing parallel in the results, but there's no mention of Boltzmann whatsoever in Sanov's paper, which is really funny historically. I mean, I think you can take this as a source of a nice historical search. Sanov at the time actually was working in Moscow. Kolmogorov was in the background. Who actually proposed the problem to him is a bit of a mystery. Moreover, this is the only probability paper of Sanov. Sanov actually was known more as someone working in number theory. So this is entirely a mystery as to why he came up on that problem and why he never actually picked up on Boltzmann. And another historical fact is, in fact, Sanov is more known as someone who was sent by the Soviet regime in North Korea to oversee the establishment of a mathematical school there. If you look at Wikipedia, and then I also had discussions with some Russian colleagues, his claim to fame is more on that front. But anyway, so this is a result that's very important in information theory, and that really is the second result that we find in the history of large deviations. Then there's not much happening for a long time until then the work was picked up again in the 70s and 80s. And this is really where the theory took off as a mathematical theory. And then people realized that the fact that probabilities are exponential is a lot more general than dealing with independent random variables or dealing with sample means or dealing with empirical distribution, or for physicists, just dealing with physical system. And this is work from Varadhan and Donsker actually that started the theory. And so at this point, what I'm going to do is just explain what the theory is about in a more general framework. So the idea is, abstractly, is that you have some random variable which is parameterized or indexed by some variable like n, and that could be the number of random variables that you have in the sum. That could be the number of particles that you have in a system. So that is your scaling variable. So in fact, what you have is a family of random variable parameterized by n, and what you want to calculate is the probability density or the probability distribution of that random variable. And so what the theory takes as an hypothesis is what we call the large deviation principle. So this is the postulate. So we'll assume, or we'll try to actually prove, that the distribution has an exponential form with that parameter n, and what we want to calculate is the exponent that we call the rate function. So here, I'm just writing as a physicist that the probability is approximately exponential, to mean that the dominant part of the distribution is this exponential, this decaying exponential with that parameter n. Now, what this means mathematically is that if you take the log, then the dominant part is really, you have the linear scaling with n, and any corrections will be sub n, so smaller than n. So if you take a limit where you divide by n, then what you recover is the dominant part, which will be the rate function. And this is how mathematically you'll see the large deviation principle being defined as a limit with n going to infinity. Mathematically, it's a bit more involved, as you can imagine. You'll be an upper bound and a lower bound, and will be an exponential upper bound, there'll be an exponential lower bound. And instead of looking at the probability density, people will look at the probability that an takes some value in some set. And so then you can look at open sets, closed sets, and then you can start dealing with upper bounds and lower bounds. But the essential idea is that there's a distribution that behaves exponentially with some parameter, and that's the scaling parameter. So that's the postulate, that's the large deviation principle. And the goals of large deviation theories, for a given system, for a given random variable, you want to prove that the distribution of that random variable has a large deviation form. So you want to prove that you have an LDP, and you want to calculate the rate function, which gives you basically all the information about the fluctuations of that random variable on the exponential scale. So that's really the dominant part of the distribution. We'll see some example. If you know the power of the exponential, then if you have corrections that are sub-exponential, they won't matter much compared to the exponential that you have in front. So the exponential really describes or captures much of the distribution and what the distribution looks like. And then we'll see some examples of this. Now, how do we get the rate functions? So there are different methods, there are different tools that you can use to do this. I'll present only two tools that we use for this. In fact, only one tool, but I'll show one intermediate result, which which is known as the Varadance theorem. So Varadhan here, Srinisava Varadhan, was given the Nobel Prize for his work on large deviation theory in 2007. This is work that actually dates from the 70s, even 60s. He had some original results in the 60s, but work in the theory mostly during the 70s. He's the one actually who defined that large deviation principle as the building stone, the founding stone of the theory itself. So we have that large deviation principle, and the idea of Varadhan, which is an idea that we encounter often in probability theory, is that instead of looking at the probability, we'll be looking at generating functions or characteristic functions. So if you're able to calculate something via the generating functions or the characteristic functions, then by inverse Laplace transform or inverse Fourier transform, then you can recover the probability distribution. And then the second observation is that if the probability behaves exponentially, then so will the generating function. So if you define a generating function exponentially with some test function f of an, this is the generating function. If the limit, the log limit of this exists, then it should mean that you have a large deviation principle. And so what Varadhan proves is that it's the other result. If you have an LDP, then this will also behave exponentially, so this limit will exist. So what he proves is that, again, if you have an LDP for the distribution and you define a generating function, then the generating function will behave exponentially. This is a kind of Laplace integral principle or saddle point integral principle. And so if you take the log limit, like we did for the rate function, you should extract a function, a constant, which is that lambda f. And moreover, it proves that the lambda f will be given by this maximization. What's interesting with this result is that if you take a particular case to be f to be just ka, so an affine function where k is some parameter, then what you end up with is that you have a kind of log generating function, so a cumulative function being the Legendre transform of the rate function. So this is interesting. It's interesting because it suggests that you can have the inverse result as well. You might be able to obtain the rate function as the Legendre transform of a cumulative function. And this is the result I want to present now. So this is the main result that we use in physics to get rate function, and it's called the Gartner-Ellis theorem. So this is a result that came from Gartner in '77 and then was generalized by Ellis in 1984. Richard Ellis was a mathematician at UMass in Amherst. He died, I think, 2 or 3 years ago, recently. So the starting point now is this idea. Just start with generating functions. So we define what we call the scale cumulative generating function. So here we have the generating function of the random variable that we're interested in. We want again to prove that is an LDP. We take the log limit, we take the 1 over n. So we have a kind of cumulative generating function, but because of the limit, we call this the scale cumulative generating function. And the theorem goes as follows. If you can calculate that lambda k without actually knowing the distribution, of course, or that it has an LDP and that lambda k is differentiable, then you have actually the two goals that you want to solve. Namely, the first one is that it means that the distribution has an LDP, so it has an exponentially decaying form with that parameter n, and the rate function will be given by the Legendre transform of that function lambda k. So I of a, the rate function, is the Legendre transform of the lambda k. So this is very powerful because you can apply this to any kind of random variable, as long as you, but the difficulty, as I'll try to explain, is in calculating that lambda k. So you have a kind of expectation you need to calculate, some kind of big function and limit that you need to calculate. And then from that point on, you can test the conditions. If you're in the conditions of the theorem, then you have the LDP, and then you have the rate function, moreover. So this is, again, the main result that we use, and I'll show you some applications of this. Okay, before I get to the physics, let me apply this to the two examples that we had before. So in the case of Cramer's, where you look at simple mean, and I'll show you also how you can also obtain Sanov's theorem using the Gartner-Ellis theorem. So let's start with Cramer's theorem. We have that simple mean with a sum of independent and identically distributed random variable. And now if we follow the Gartner-Ellis theorem, we should calculate that lambda k. What is that lambda k? Again, it's the generating function, the log, the limit. But for IID random variables, everything simplifies massively because there's no correlation. So the random variables are independent. So the product of exponential will factorize. They're identically distributed. So the limit disappears. And what you're left with is that the lambda k is the cumulative function of one random variable. So that's easy to calculate. You can take your favorite distribution. If you have a sum of Gaussian, you can calculate lambda k. It's a parabola, it's differentiable. You can take the Legendre transform. It's also a parabola. And so you get now the rate function for a sum of Gaussian. It's a parabola. And so it means that the distribution of a sum of Gaussian decays exponentially with the number of random variables, which means that it peaks somewhere. It just decays exponentially, and then the rate of decay is given by the rate function. Now here I show the rate function with having 1, 0. In general, the rate function is always positive. It has 1, 0, and under certain assumptions. In this case, you can prove that it has 1, 0. The 0 has to be the mean because we know that the sample mean converges in probability to the mean. So we have in the LDP actually that very property. The fact that the distribution decays exponentially means that if I look in the tail will just go down exponentially as the number of random variable grows, which means by a conservation of probability that it has to peak somewhere, it will peak at the 0 of the rate function where the distribution does not decay exponentially. So the 0 is associated with the law of large number. This is where you have a concentration of probability, and this is very important. So the large deviation principle gives you information about the shape of the fluctuations, if you want, but also where it concentrates. So it gives you information about the typicality, the typical value of the random variable that you look at, and then the very rare fluctuations around it. In this case, the fluctuations are Gaussian because the rate function is a parabola. So if I put this in the exponential, then I get a Gaussian. If you take another distribution for the random variable, for instance, exponential, then you can also do the same game. You calculate lambda k, you can take the Legendre transform, and now you get this rate function in red, which is not a parabola. And now from this, I can see, okay, there's 1, 0, so the distribution will concentrate exponentially there. This is the law of large number. In the tail, it's not a parabola, it's actually asymptotically linear. So I know that in the tail, I have asymptotically exponential fluctuations. But near 0, I get something that's very different. This actually diverges like 1 over s. And so here I have logarithmic fluctuations close to 0. So again, you have this idea that the rate function gives you basically all the information, all you need to know about the distribution, but on the log scale, because that's the important scale. Any corrections to this will be kind of non-important with respect to the large deviation result that you have at hand. Okay, so these are two simple examples. And again, they're simple because we have that ID property, so the limit simplifies, but the Gartner-Ellis theorem is actually general for any kind of random variable. It doesn't assume that the random variables are independent, and the whole theory, of course, does not assume that random variables are independent, and this is the beauty about the theory. I'm going to skip over this calculation quite quickly, so if you're interested here, I'm just doing the calculation, Sanov's calculation using the Gartner-Ellis theorem. So you have n random variables. Again, you're looking at the empirical frequency. This is the random variable that you're interested to calculate the probability of. You can follow the multinomial route that Sanov used or Boltzmann used, but what you can do instead is use the Gartner-Ellis theorem. So you calculate the lambda k. The only difference here is because you have a vector for your random variable, k will be a vector as well. You can take a vector Legendre transform, and what you get as the rate function is the relative entropy directly. So here there's no combinatorial argument. It's just a analysis calculation based on Gartner-Ellis to get information about the probability distribution. So the Gartner-Ellis theorem is quite powerful, but also very simple in the way that you're doing a probability calculation without really thinking about probabilities. Okay. Now, the theory, of course, as I mentioned just before, applies beyond independent random variables, and it wouldn't be a theory if it did not. And this is really where the nice work of Varadhan and Donsker. Donsker was Varadhan's supervisor, basically. This is where the work emerged. So in the 70s, they showed that you can apply the same ideas to Markov processes and processes involving many particles, as long as you have a Markov property. So in this case, here's a generalization. You can think of a Markov process now, and instead of looking at a sum of random variable, you can look at the integral in time of a function of the state. And so that plays the role of a sample mean if you want. And then we know from the ergodic theorem, if you're dealing with an ergodic Markov process, that random variable will converge in probability in the limit when t goes to infinity, the observation time goes to infinity. And what you can prove using large deviation theory is that, yes, you have that concentration, and that concentration, again, is ruled by an LDP. The probability distribution of that random variable decays exponentially with time, capital T, and there's a rate function that you can calculate explicitly from the theory. It's a bit, you can use Gartner-Ellis theorem for this, or you can use other results that were developed by Donsker and Varadhan in the 70s. So this is known as the Donsker-Varadhan branch of the theory that's dealing with the ergodic limit. There's another theory that emerged right about the same time where the limit is a bit different. So here you also consider a Markov process described by a stochastic differential equation. So you have a differential equation that you perturb by a small Gaussian noise. And so here the scaling parameter is the noise amplitude. So you're not looking at sums of random variables or integrals of random variables, but you're looking at kind of deterministic limit of a noisy system where you just put the noise to zero with epsilon going to zero. What you can show in this case is that the probability of a whole trajectory will go down exponentially with the noise. And this makes sense if you think about the LDP actually describing a kind of concentration. If you have a noise perturbation and you're putting the noise to zero, then the behavior, the whole system dynamics will converge towards the deterministic dynamics described by the differential equation. And this is what the distribution actually will tell you. The probability of the trajectories will just concentrate around the deterministic trajectory of your system. And this is the low noise limit. So this is an entirely different limit, scaling limit, but you still have that property that probabilities behave exponentially. And that was worked up by two Russian mathematicians, Friedlin and Wenzel, in the 70s. And this is an interesting physical connection. If you're coming from physics and you're looking at this result, this is very reminiscent of what we call the Onsager functional, or the Onsager-Maklub functional. And so this is an idea that was worked out actually already in the 50s of describing probabilities of trajectories and a low noise limit. And Onsager and Maklub were looking at escape problem when the noise goes to zero, kind of metastability escape problem. And they get the same result by non-rigorous means using physical arguments. But the result is very much the same. So these are kind of two branches that go beyond IID, and they're very much applied these days to study different applications, different systems. So on the physics side, you can apply ideas about the low noise limit to study metastability or escape problem. You can also use that low noise limit to study Rugg waves in turbulence. So that was done recently by Erik van den Eyden in New York. So this a bunch of interesting work actually in looking at probability of rare events and stochastic partial differential equations. So describing kind of toy models for describing Rugg waves. So waves that are massive, large events whose probabilities are exponentially small with some scaling parameter. But applications go beyond physics. So this is being applied also in queuing theory. For instance, you might want to calculate the probability that a queue has some overflow, and then often it behaves exponentially with some scaling limit. It's also used in statistics and estimation theory when you look at fluctuations of sample means or estimators in general. And as I mentioned before, it's used in information theory. Sanov's result, for instance, is the basis of the Shannon compression theorem for IID sources. And then you can put some correlations, and it's basically applying large deviation to Markov processes. So that's, I'm going to stop really just explaining what the theory is about. I just wanted to emphasize the main result here, which is the large deviation principle, this idea that for many systems, not all systems, this is not a universal property, but this is a general property, and then we have tools or results or conditions actually to say that a given system or a given random variable will have a large deviation principle. So its distribution will behave exponentially, and it's quite large in terms of application. So it's justified in a way to build a whole theory on this approximations of probability distribution. And the main points to take out of this is that the rate function, again, gives you information about the distribution. And the main information that you want to know, again, because you have that exponential dominant factor approximation for the distribution. And again, the rate function will be positive in general. We'll have 1, 0. That 0 is where the probability distribution will concentrate. So that corresponds to the law of large number. Often locally around the 0, it looks like a parabola. So locally you have Gaussian fluctuations, and that can be related to the central limit theorem. But the main point of large deviation theory is that in general, when you calculate the rate function, you can get very funny rate function that describes fluctuations that are not Gaussian. And here I'm putting like a very extreme example where the rate function might look like this. And then you say, okay, there's 1, 0. So there's a concentration point here, but there's a region where the probability here is slightly more, it's bigger but it's not a zero, so it will go down exponentially, but not as fast as this region or this region. So this picture actually describes what we know as metastability. You have a state that decays in probability, but not as quick as other states. And the final word I probably say about this is that it's not just a theory of fluctuations, you have the distribution, it's also a theory of typical state. So often the theory is used not actually to look at fluctuations, but to determine what is the typical state of the system, what is the zero of the rate function. So it's often used in that direction. Okay, so that closes my mathematical introduction. Just gonna try to keep time here. And what I'll do now is to try to explain how it's used to study physical system. And I'll start with the equilibrium system. So an equilibrium system is a system that doesn't have any energy input or output. You're not doing work on the system. So it's just a system left on its own. So you have, how we describe this in statistical mechanics is that you have n particles, and then I described some of the words before. You have a microstate, so that's the microscopic configuration. So if you were able to zoom in or have an ultimate microscope where you could look at all the individual particles, you would be able to trace what is the state of each particle. So that what we call this the microscopic configurations or the microstate. Now, the realization in statistical mechanics is that you're not able to have that level of information. You're not able to track the system in its exact state. So you're doing statistics on the system instead. And so you introduce what we call a statistical ensemble, which is really just a probability distribution on the microscopic configuration. You're just saying, how likely am I to see a given microscopic configuration? And there's some physical principles to actually write down that probability distribution. And I'll say a few words about this in the next slide. And again, just like Boltzmann and Einstein, what we're interested in is not, again, the microscopic configuration, but something that we can observe on a bigger scale, like the total energy of the system, the total magnetization, or the energy distribution. And then we call this the macroscopic state or the macro state. And the goal of the theory is to calculate the probability distribution of that macro state. So the probability that I get a certain value, that I see a certain value for the microstate, is the sum of all the probabilities of all the microscopic configurations having that value of microstate. So that's the basic mathematical framework. But this is a huge problem. So we want to calculate the distribution. If we're able to get this, then out of this, we can calculate the most probable value of the macrostate. This is the equilibrium state. This is the state that you'll see in the lab. And then we also want to study the fluctuations around that equilibrium state. And now, the reason why we can apply large deviation theory to this particular problem is because we have a scaling limit. This is done by taking the limit when the number of particles goes to infinity. In physics, this is what we call the thermodynamic limit. The reason why we take that limit is that we're dealing with very big systems in terms of particle numbers. We're dealing with something like the Avogadro number, so 10 to the 23. So if you want to deal with a system like this, instead of just fixing the number to be large, you just take limits everywhere, and then you'll get quantities that are actually representative of a very big system. And this is the idea behind the thermodynamic limit. Okay, so this is the framework. Now, once you start applying large deviation theory for this, then you have to specify what is the underlying distribution for your microstate. And this is where we define that notion of statistical ensemble. So the first ensemble that was defined and worked out in terms of entropy or large deviation properties was the microcanonical ensemble. And this ensemble in physics describes a system that has a fixed energy. So you have many particles, they're enclosed in some container, which is insulated. And so the energy of that system is constant. So the energy in this case is a parameter. So the probability that you want to calculate for the macro state is parameterized by the energy. If you change the energy slightly, you're likely to change the distribution. And what you can show is that for a system like this, the probability will go exponentially with the system size, the number of particles, and then the exponent will be the entropy. It's the rate function, which, as described by Boltzmann in 1910, he described as the entropy. So he postulated that the probability was exponential, but because we know entropy goes like the number of particles, what he was postulating was really the existence of the large deviation principle. And now what we can do with large deviation theory is not use this as a postulate, but actually prove using a model that the probability does behave exponentially with the number of particles. And then we can test, we can actually calculate explicitly, we can verify that the rate function is the entropy as calculated by, as postulated by Boltzmann. So this is if you have a fixed energy. for your system. There's another very known ensemble in statistical mechanics, which is called the Canonical Ensemble. It was introduced by Boltzmann, but the probability side of that ensemble was worked out by Landau, physicists in the 30s. So here, your system doesn't have a fixed energy, but it's connected to a reservoir with a fixed temperature. So your system has a fixed temperature. In this case, the parameter to use is not the energy, but it's the temperature. Here I'm putting the inverse temperature beta, but you have the same thing. The probability of the microstate that you consider will have a probability distribution that decays with the number of particles. And then what controls the fluctuations of that microstate will be a rate function that you can calculate explicitly using the methods of large deviation theory. And the methods are actually surprisingly very close to what Landau was describing in his paper in 1937, and very close, in fact, to the methods that were used in statistical mechanics. So what I'm doing here is a kind of rewriting of what physicists know in statistical mechanics, but in the language of large deviation theory. And what physicists would say is that for the microcanonical ensemble, probabilities are determined exponentially by the entropy. And here I call the entropy the rate function. And for the canonical ensemble, physicists would say that probabilities are determined by the free energy. And the free energy is extensive with the number of particles. And so that leads us to saying that the probability is exponentially small with the number of particles. And I call this the rate function again, but here the rate function is what physicists call the free energy. And out of this, you can get what we had before. So there's an exponential concentration of probability. You have an equilibrium state that emerges as the zero of a rate function. That state is exponentially probable, more probable than any other state. And this explains the stability of microscopic system. If you look at your table and then you put your finger, you don't feel energy fluctuations of your table. You feel the equilibrium state of your table. And the reason why you don't feel fluctuations is that these fluctuations are exponentially unlikely. And you have to imagine that n is the Avogadro's number. So it's 10 to the 23. So the probability is exponential 10 to the 23. So it's amazingly small. So the equilibrium state is overwhelmingly probable on the exponential scale. And this is why we have exponential, we have thermodynamic stability of objects. You'll never see a fluctuations of a table, unless the table is very small, composed of just a few atoms. And then now you can start seeing fluctuations. And people start doing this now more and more in the lab when you look at biological systems like cells or even nano engines or nanosystems. But this is a totally different story. Okay, so this is just to give you an idea how this is applied. The ideas are the same here. I have a calculation that takes again the idea of Sanov to calculate an equilibrium distribution for the perfect gas, but I think I'm going to skip this. If you're interested, you can ask me a question or you can have a look at the slides. I'm just going to mention now for equilibrium systems, this idea that you can apply large deviation theory to study equilibrium systems came again, and I think I mentioned this at the start of the talk, in the 70s. So the first work on this is from Oscar Lanford in the 70s, who actually laid down using tools from large deviation to really study statistical mechanical systems in the way that I just presented. And then from that point on, it was applied to many different systems like spin systems, Bose-Einstein condensation, turbulence, and then it's still being used right now to study the properties of equilibrium systems. This is where I started myself, actually. So I did my PhD on using large deviation theory for describing equilibrium systems. And the nice thing that you realize, again, which I want to emphasize, is that probabilities, when you're dealing with equilibrium systems, all probabilities have this exponential form. And this is really the basic form. This is really the important fundamental form for doing statistical mechanics and thermodynamics. And if you think about how entropy is defined or free energy is defined, there's always a limit, which is a thermodynamic limit. And there's always a log floating around. And the reason why you have that log is because you have a large deviation principle in the background. And that theory is useful because it describes, again, the typical states, equilibrium states, but also fluctuations. I'll give you some references at the end if you're interested by these applications or the history of the subject. So I mentioned this is what I did in the PhD, but what I'm doing these days is not studying equilibrium systems, but non-equilibrium system. Now, what is a non-equilibrium system? And I'll finish with that part. I hope I think I'll be on time. So a non-equilibrium system is a system where you have energy input and outputs. And the main example that we have in physics is you have a system with two energy reservoirs or two temperature heat bath. So you have a hot system here and a cold system here, and then you put a metal slab in between. And because you have hot and cold, there'll be an energy flow actually in the metal slab in between. And this is a non-equilibrium system. There will be a steady state system. You'll see that there's a distribution of energy actually flowing there. But it's non-equilibrium because you cannot describe this using equilibrium ensemble or techniques that were developed for equilibrium systems. So there's a kind of explicit time dependence here. You're forcing the system away from equilibrium with either an external force or reservoirs like this. So the way that we model this now is that we take an explicit time picture. So we really replace models that are static, which is the framework for equilibrium statistical mechanics, and then we replace them by Markov processes. So we're dealing with stochastic process. So now I have a process, the state is X, and now it's parameterized by time, so it's X of t. This could be a one particle process, it could be many interacting particles evolving, but the basic assumption when we do mathematics about these systems is that we assume that we have a Markov process. So the evolution of the state satisfies the Markov property. And again, physically, this can describe a system that's being forced by external forces or potentials, or it has boundary reservoirs that are responsible for the driving. But the idea now, so the framework is slightly different in that we're using now stochastic process, but the idea is the same as before. We have now probabilities on the trajectories, and we still have this notion of observable. We're not concerned with the probability of each trajectory. So this will be the microscopic configurations. No, so we want to look at some observable quantities like the mean current or the current in the system, and that's the observable. But now the observable is slightly different. It's more complicated because it might depend on n particles. It might be integrated over time, and it will depend in general on the trajectory, on the full trajectory of the process. So this is why I'm putting the square bracket X here. The problems are the same though. So ideally what we want to do is for a given observable, we want to calculate the probability distribution. And out of this, we want to calculate the most probable value, which we will call the stationary state. And we want to study also the fluctuations around the typical values. But as for equilibrium, we're often faced with a scaling limit. So either we have a large system, so we can take n going to infinity, or we have a long observation time, so this will be a kind of ergodic limit, or we could also look at a scaling limit where the noise of the system goes to zero, if you can actually identify a source of noise into it. And what we're expecting is that we don't want to calculate the probability distribution exactly. That defeats the purpose again. It's very difficult, if not impossible, to calculate distribution exactly. What we anticipate is that there's a large deviation principle, so there's a general exponential form which is easier to attain. And so that's the goal of the theory. And indeed, that's the case for many systems. And I'm just going to show you one simple system where people have done this. So this is a physical system that's been realized in the lab in many, many places in Europe, in the States. You can actually buy this kind of system off the shelf now. So what you do is that this is what we call the laser tweezers or Poole-Brannan particles. So you put a micron size glass bead in water, and then with a very good microscope in a camera, you can track the motion of that bead in the water. And if it's small enough, what you'll see is Brownian motion. So these days, actually, I think even for undergraduate labs and physics, this is a good demonstration to show Brownian motion to students. And so the Brownian motion itself is an equilibrium system. It's not being forced by anything except the water, which acts as a noise source. But what you can do is that you can shine now lasers onto this glass particle, and then you can start pulling the particle in some direction. So you can do some work on the particle, and that becomes a non-equilibrium system. And this is all, you can describe this in some limit. Physically, it's the low intensity limit for the laser tweezers. So you can pinch the particle. So this is why it's called the laser tweezers, and then just drag it in water. In some limits, you can describe this using a stochastic differential equation. So a kind of Lagrange dynamics. So this is the acceleration of the particle. This is the viscous drag from the surrounding liquid. This is the spring force. So effectively, when you shine the laser and then you start pulling, the laser actually acts like a spring force. And this is the noise term coming from the surrounding environment, the water. And so you have now a stochastic differential equation. This is a Markov process. And what we're interested in is not so much the trajectory of the system, but we want to calculate some physically measurable quantities, like the work that you do on the particle by pulling the particle, and the work can be transformed into potential energy or heat being dissipated by the particle and the environment. So these are physical quantities. Mathematically, they are random variables. They're integrated random variables in time. And so if you try to calculate the distribution, what you realize is that the distribution of any of these quantities will have a large deviation form. And the scaling parameter now is the integration time. So what you do is that you calculate the work over a very long time, and then you see that the work that you do concentrates on some mean work that you do. But you have exponential fluctuations, so you have tiny fluctuations of work that are described by the LDP. So there are fluctuations of work, for instance, which are, even though you're pulling the particles, because of the water surrounding, the particles would actually pull back the laser, and the particle can actually go backwards, even though you try to pull it, and that's because of the noise source. And this is exponentially unlikely, as described by the large deviation principle. And something interesting that physicists like to study, what they call fluctuation relation. So for many systems, you have specific symmetries in the distribution. So for instance, for this particular example, if you have a look at the probability of a positive work fluctuation over the probability of a negative work fluctuation, you see that it's exponential with something that is linear in the exponential, and this is called a fluctuation relation. And that comes as a result of the large deviation principle. So there's there are many things you can infer from the rate function, including that fluctuation relation, which is a very strong symmetry actually for the work fluctuations. Okay, so this is just meant to give you an idea out of the equilibrium box, how we can apply tools from large deviation theory to study something that evolves in time with noise, but you can go a lot deeper into this and a lot wider also, because there are many applications. So here I'm just listing some applications. I don't want to discuss them all. It's more like a blank list, but a lot of the work that is being done right now in non-equilibrium statistical mechanics, but also in large deviations theory, is to study non-equilibrium systems composed of many particles. So what people try to look at is, again, this very general system where you have a heat current between two temperatures, and then you want to come up with a stochastic model for that situation. And so what people do is this picture I put there. You imagine that you have tiny particles carrying the energy from one side to the other, but the evolution of each of these particles is random, and so it's described by a Markov process. Now they can collide, you can have some exclusion, also interactions between the particles, and then you can add that to the Markov process. And so in that sense, you can deal with very complicated Markov processes describing non-equilibrium systems, and then you can start doing large deviations on those systems to calculate what will be the mean current, the stationary current, and what are the fluctuations also around that mean current. So this is the subject of interacting particle models. So if you know anything about the exclusion model, the zero range process, it goes in that line. So there's a whole slew of literature on this. I also mentioned metastability, the thermal activation, also Rugg waves. This goes in the sense of, if you look at the state of a particular system, you want to calculate the probability that it goes away from the stable state. And often it goes exponentially, say, with the noise amplitude or the temperature. So kind of large fluctuations away from a stable state will be exponentially small. So the probability of a large fluctuation will be exponentially small with the inverse of the temperature. And then there are other applications to disordered systems like random walks and random environments. I think Jean-Luc has worked on multifractal in London. I think we discussed this. If you look at the mixing of fluids, you can have multifractal distributions that are also described by some exponential distribution. There's a scaling parameter also in that case. Other applications, chaotic systems and quantum systems, not surprisingly. And what ties all these applications, again, is this idea that you have rare fluctuations that are exponentially rare with some parameter. You want to describe this using tools that are just easier to use than calculating the distribution exactly. And what's interesting for a physicist is that you have the same theory to study equilibrium and non-equilibrium systems. So that's always been a big goal, if not a dream of physicists, is to describe non-equilibrium system on the same footing, using the same tools as equilibrium system. And this is something we can do now. I think I'm going to stop here. So this is, I'm giving you for the last slide a summary, a kind of dictionary of words that physicists will be using versus words that mathematicians will be using, like a random variable for physicists will be a kind of probability distribution or an ensembles. And in the time-dependent context, it's a stochastic system. Most probable values for mathematicians will correspond to physicists to equilibrium states or stationary states. And then you have other correspondences. One that I haven't mentioned in detail is the idea that the rate function is an entropy and the cumulative function is a free energy. And this is very deep, actually. This is a very deep connection between thermodynamics and large deviation theory that I explain in the paper down there. And again, what you need is always a scaling limit. You cannot go around this. You need a scaling limit to actually define what you mean by this approximation and the fact that you have a dominant exponential form. And again, the scaling limit is up to you. It depends on the system that you study. And again, what's interesting for physicists is that you have this unified language for statistical mechanics that can be used to study equilibrium and non-equilibrium systems. If you want more information about this, so this is a talk that I've given quite a lot. I like giving this talk. I'm not talking about myself, but just about the history of things and the interesting history. But if you want more details, I've written in 2009 when I was in London a review paper on this, where you have 69 pages on equilibrium systems and non-equilibrium systems. I wish I could update it right now. It's not up to date, but I think it's a good starting point. And more recently, I've written lecture notes for summer school in 2018 that describes more the Markov process side of things. And so this is lecture notes that were published in Physica A, and then you have the reference there. I have more papers on my website if you're interested about non-equilibrium applications, and the URL is there. So on this, I'll thank you for your attention.
Thank you, Hugo. Are there any questions from the audience?
I have a really simple one. I really enjoyed this talk. Thanks a lot for visiting from such a great distance. What would be, I'm sure there are many simple examples, but what would be the simplest example of one of these metastable, so-called metastable distributions, or a system that generates one?
There are many. One, I think that it's like Ising, if you take Ising spin models. If you look at the state of the system close to a phase transition, then you can have metastability where you have coexistence of the spin pointing in one direction and the spin pointing in the other direction. And then in this case, you have a rate function that looks a bit like this, where now, in fact, the rate function has two minima. So you have two very equally highly probable states. And as you change the temperature, you start favoring one state over the other. So that's the good example of metastability. And then you have a barrier in between, which is basically the exponential barrier that the system will have to cross in order to go from one state to the other. And so that, in physics, that's what we call the free energy barrier. But you also have dynamical example of metastability where a system can go dynamically between one state to another. For instance, when you have intermittency and things like this.
There's a question in the chat. Nagesh was asking, after the talk, could you kindly share your historical insight into the notion of IID? Maybe how it fits within the historical framework.
Again, what's the question? Sorry, Jean-Luc.
The question is, after the talk, could you kindly share your historical insights into the notion of IID, of independently distributed?
Well, IID is always the starting point of everything because it's the simplest context, of course. So for many years, actually, I mean, the start of probability theory for 50 years was dealing with IID random variables. To some extent, also probability theory still deals only with IID random variables because it's very difficult to go beyond this. So IID is the perfect gas analogy for physicists.
I mean, I wanted to know because the notion of independence somehow has to involve probability, and then probabilities. There seems to be like a chicken egg dependency of like what an independence means, because the notion of independence somehow has to invoke probability and vice versa somehow. I just thought if there is any break in that cycle or not. Maybe I'm thinking about it.
Well, mathematically, independence is just the factorization of probability. So I think that's not controversial. Then to test whether you have independence, this is an entirely different story, of course. If you have a system that you try to modelize, if you try to come up with a model of a system or try to verify whether a system has independent particles, this is a different thing. But as if you start with a model just to say that you have independent components or independent random variables, it's just to say that the probability factorizes into marginals.
I guess I was thinking about the latter, like how do you test them?
Oh yeah, no, testing is something else. It's very, I mean, quantum mechanics is this is a whole subject for quantum mechanics actually also. I mean, it's just not specific to.
No, your historical nature of it, it seemed like you had deep historical insights into these things, so I asked that question.
No, I'm not so sure how. I mean, I think the notion of independence was known for a very long time now. Whether, again, it's a difficult question to test whether you have independence. This is actually something I discuss a lot with students. I teach probability statistics for first-year students, for the science students, and then we say, okay, good enough that you coin tossing, you have independence, but why do we have independence? And then
right. I guess, yeah.
We can discuss for hours on this. Yeah.
Thank you so much. Thank you so much.
So I had a quick question. What is an example of some macro variables that you might track for non-equilibrium systems?
So if I go into, so this system, for example, if I look at this system, so this is the microscopic, see, I think Jean-Luc will relate to this, but for us French speakers, microscopic and microscopic are very difficult to distinguish. But so there's microscopic and macroscopic. But so this is the macroscopic picture of the system. Two temperatures, you have a current in between, but the microscopic picture of it is that you have the little particles actually moving from one side to another. So here the observable could be the number of particles crossing a certain cross section over time. So that will be physically proportional to the current, the total current that you have over time. So this will depend on the number of particles you have, but also the observation time that over which you do the observation. So in non-equilibrium, people look a lot at currents. So current is really the defining feature of non-equilibrium systems.
I see. It's an equilibrium quantity, though, right? In some sense, it's still an equilibrium quantity, just at a next order in some sense.
Yes,
right?
yeah.
I see. Interesting. So in other words, the two basins that you have in your picture there are assumed to be large enough that this current between the two is essentially steady.
Yes, yeah.
I see. That makes sense. Is there much room for large deviations? Like, in quantum mechanics, you describe the motion of particles as, the semi-classical limit, right, is assuming the most likely path of the quantum particle, and then you have fluctuations around that, right? Mm-hmm. So basically, that's path integration.
Yeah.
But does path integration have a large deviations aspect to it? I mean,
well, the semi-classical approximation has one. It's kind of a low noise theory when you take h bar going to 0. So when you extract classical mechanics out of the Feynman path integral, so that's a kind of low noise limit. And in fact, actually, the two Russian mathematicians who worked on that low noise limit for stochastic differential equation, in the introduction, they mentioned that parallel. So it's something that was known as a kind of functional saddle point approximation, right? And that's the basis also of a lot of calculations that we have for large deviations. But there are ways to do quantum large deviations in the purely quantum domain without doing semi-classical approximations or like they do in optics, for instance. But so you can take like a fully quantum system, and then from the quantum description, you can calculate probabilities for certain macroscopic observables. So that's being done actually more and more. There's a lot of activities actually now in the US, especially around non-equilibrium quantum systems, so evolutions of non-equilibrium quantum systems, but also stationary quantum systems. So they're driven in stationary states. Mm-hmm. It's quite complicated, I must say. It's not something that I've dabbled myself in.
And then do you remember? You probably know the work of Jacques Van Ness and Alexandre Zella, right, on fronts. Yeah. So how does that fit into your picture when you put the categorizations of the different types of applications?
Yeah, if I remember, for Jacques, I think it's closer to what you were doing. No, it's mixing, and then you have the scale is like the observation scale, like you would define also in multifractal analysis. No?
Oh, and maybe we're probably talking about a different application. What they were doing is front dynamics in a PDE.
I know
And
this.
in front of the front, you get very low probabilities, but you need something, right, for combustion problems or something like that. It really doesn't matter whether it's 0 or, you know, whether it's 10 to the minus 26 or 10 to the minus 6 makes a big difference, right? So they use a kind of large deviation principle to look at these front dynamics.
And I suppose that will be related to viscosity solutions of PDEs or things.
Yeah,
like
exactly.
Yeah, so there's a parallel into this. Like if you look at like the low noise limit for stochastic differential equation, you can also view it as a viscosity limit for the Fokker-Planck equation. And out of this, then you have like WKB analysis of PDEs, and then you can push it further then for PDEs like turbulence, combustion PDEs, and then you do viscosity limits also. And then so you have, then it's more like you have it, the WKB expansion of the solution looks like a large deviation principle.
Ah, okay. Okay. Well, if there's no other questions, thank you so much for staying up until, what is it, 11 at night right now?
At 11:30.
11:30 at night. Oh my God. Thank you so much. Sorry that I got it off by 1 hour.
No, it's like lockdown. There's no way I can go partying in town.
That's right. Thanks very much, Hugo.
Okay, good. Have a good weekend.
Yeah. Did you want to stay and chat a little bit, or did you have to go? Do you want to go to bed?
No, I can chat a bit to you if you want. You could just like stop the recording.
Oh, yes. Thank you for reminding me.